Hello, so my name is Benoit Leveau and I'm head of pipeline at Milk VFX. I'm here today with James Reid, our head of FX, and CG Supervisor on Adrift. And we're here to talk to you about the challenges of rendering large-scale ocean simulations and how we leverage the cloud to achieve our goals. So first, a few words about Milk. So we recently celebrated our 5th birthday, and over the summer we doubled the size of our London office and now reaching a capacity for 250 artists across our 2 offices, so one in London and one in Cardiff, both in the UK. So some of our latest projects include TV series and feature films such as Altered Carbon, Annihilation, Electric Dreams, Kingsman 2, The Alienist, and obviously Adrift, which will be the focus of today's talk. So let's have a look at some of the examples of our latest work.
So, yeah, as Benoit said, I'm going to talk to you about the project. I CG souped the project, so I'll talk a bit about what it was like to work on more of an artist level, and some of the things that I find interesting that sort of cropped up along the way. So Adrift is a lost at sea survival drama. I'd describe it as a small budget movie. It was about $35 million, but it had big budget ambitions. The director's vision was for a photoreal, raw, gritty feel to the movie. And he really wanted it to feel like we were with these guys as they got caught up in a big hurricane in the Pacific. So Milk's role, we were the primary vendors on the movie. So we got to do the tricky stuff. So we got to do the big hurricane, the big storm sequences. As well as that, we did some aftermath shots and then a bunch of other a collection of 2D shots that were sort of sky replacements and cleanup kind of shots. Our expectations, so we were expecting to be provided with a boat, in these hurricane shots, a boat that was on a gimbal, filmed against green screen, and we'd be layering this into various shots from with the live action in the foreground, some blending to fully CG. And we knew that there were going to be, in this mix, some really long, challenging shots. It's worth mentioning as well the timescales involved for us. So whilst we had a reasonable R&D period, so about 5 months of R&D at the head of the project, we had a lot tighter turnaround for shots. So from turnover to final delivery was probably about 4 months. I think it's also worth, so we kind of knew we had a big challenge ahead of us, and I think this wasn't just due to the technical complexities that we were going to face, it was also because of people's own familiarity with how an ocean should look, and I don't think there was going to be any hiding from any bad CG there. So just going to play our breakdown reel of Adrift and then talk a bit about our pipeline and some of the interesting challenges that we faced. Okay, so at the heart of our pipeline was going to be the way we built the ocean and all of the simulation work associated with it. So we knew it had to be, we were going to approach that in Houdini, and therefore Houdini was going to be at the heart of our shop pipeline. Houdini has a great set of ocean tools to start with. That definitely doesn't mean everything works out of the box, because it didn't for us in the situations that we were using it. However, Houdini has got a nice open architecture for the artist to be able to develop things further where needed. It also has a great way of storing oceans in the form of ocean spectrum data, so it's nice and procedural and therefore light and efficient. And we wanted to leverage this throughout the pipeline. At Milk, our animators work in Maya, so we needed a way of being able to generate this native Houdini ocean data in Maya. So we used Houdini Engine, and we built a set of tools for a Maya animator to be able to sculpt an ocean and drop in hero waves. We kind of worked backwards. We got the plates and we had to make an ocean to fit it, which was a bit of a challenge, but fairly successful in the end. Then going downstream from effects, we've got lighting and rendering, and so we're harnessing this ocean spectrum, and we're staying within Houdini, and we rendered it in Mantra. We felt that if we were to move away from Houdini in this case, we'd be generating huge amounts of data with these long shots in the form of displacement maps. We also felt there would be a compromise potentially on quality. And of course, we're using the cloud to render. So it's super important that we keep things as efficient and light as possible. Ultimately, the less data you're passing around, the more reliable the results are going to be. The reality of our pipeline, it put extra stress on the system, that it wasn't linear. Often you had to go a few stages down the pipeline before you realized, oh, this needs changing. And so there was a lot of reworking of sims, re-rendering of stuff. So we had to stay flexible and agile in the way we were working. I'll now look at a few department-specific challenges, interesting points. So animation faced a big challenge in the form of complex camera moves in these long shots. The shot that's playing here is one that we all referred to as the pitch pole shot. So for people that don't know what pitch poling is, it's when a boat somersaults over its axis, which happens here in the heart of the hurricane. This shot was shade under 3,000 frames long, and it consisted of 4 stitched pieces of live action and some fully CG sections as well. In total, we had 7 stitched together cameras. This has just transitioned into a second piece of live action. We're about to go into a third piece as the stunt double tumbles around inside the cabin, and then fully CG, and then there's a final piece of live action as the character sinks into the water at the end of the shot. So it all had to work in world space for it to be a seamless process in lighting and in effects, and was generally a great deal of fun for the animators to work on. It was kind of the first shot that we were fully aware about, and pretty much the last one to deliver as well. That's about where it ends. The next thing to mention, and this is something that a lot of the departments experienced, it contributed to the non-linear process in shot work, and it's this concept of detachment from what the final result is. This isn't actually one of the worst examples, but I think anything that's heavy in effects, and in this case, render time displacement, it's quite hard to get an accurate approximation of what it's going to look like in the viewport. Okay, some of the effects challenges that we faced. The effects was all based around a guided layer flip simulation. So that's a band of particles, a patch of particles in your area of interest. So in our case, around the boat. In my very contrived example that I've built here, you can see the first problem that we came across. The surface, the layer of particles has to stay fairly true to where the procedural ocean wants to be. And we saw that in these big these slow-moving swells, the particles tended to slip off the surface. We had to think around this and come up with a couple of solutions, which we did in the form of applying 2 little adjustments. The first one, we came up with a method of detecting when these slumped particles were too far away from where they should be, and we calculated a corrective velocity, which we applied alongside the Houdini guiding velocities. This worked hand in hand with a custom gravity direction as well. So we defined gravity, instead of being vertical, as perpendicular to our big ocean waves. As we were working with these simulations, we were looking at a ton of reference, and we kind of felt that we weren't getting enough energy to the sim. At this stage of the R&D, we didn't want to be dialing in per shot extra velocities and other ways around it. So we wanted to get to the heart of why this was happening. And the biggest contributing factor we felt was the layer depth. With a bigger layer of particles, you got more particles to throw around, and we got bigger splashes suddenly. Had two downsides. One was longer sim times, and the second was you get bigger splashes everywhere. So further from the boat, where perhaps you want it to be truer to where the procedural ocean surface is, it was harder to control in those areas. So we kind of had to find the right balance of layer depth and the other factors. Once we're happy with the simulation, we had to create something that we're going to pass on to lighting. So we had to mesh that patch of particles, and the suggested method was to blend it down to a y=0 plane and extend out to the horizon. You can see this causes quite significant warping around the bound areas in these big wave scenarios, and we realized this was due to when you're blending down to y=0, you're not fully taking into account the x and the z components of your ocean displacement. So we came up with our method of doing this, which was in the form of creating a low-pass surface. So we extended the polygons out, and they were of enough polygon density to be able to resolve the lower frequencies of the ocean, which we did. And then the final detail was the higher frequencies, and therefore the fine detail of the ocean was still applied at render time. Whitewater detail plays a huge part in bringing it to life, adding a lot of energy into it, making the storm seem violent and believable. We spent a lot of time looking at webby patterns that form in turbulent water. And I think an interesting point to mention here is that the shot that's playing in the bottom right was our R&D shot before any shot turnover, and we kind of progressed this up and up and up, and it ended up being used in the final movie, which was quite satisfying. The last part of the ocean effects was the foam, the wide ocean foam layer. We kind of studied this almost like a living organism with a life cycle. So we were looking at it with from its birth through its emission as peak spray on the energetic tops of the waves, and then as it settled back onto the surface as foam and then disintegrated naturally. This gave us huge challenges in the project, trying to get this looking believable and working right, looking natural, not appearing, not popping on in unnatural ways. And the heart of the problem here was being able to track the ocean surface in a meaningful way. We had a breakthrough with this where we'd switched over from looking at the big global values across the ocean to considering proximity around each point. So you're considering more local attribute values. By that I mean you might have a low area of the ocean surface, but it might be still doing choppy, violent things, and you want interesting stuff to happen. So we came up with a set of criteria based around local height, local curvature, and local velocity to create these nice emission areas. The last piece of the puzzle really then, in terms of the look of the ocean, was extending out what we could really do with dynamics. So we came up with we studied again a lot of this foam. We spent a lot of time looking at foam and white water on this project, and we came up with some nice noise patterns that were procedural, and we got at render time to give the illusion that our dynamics were extending out to the horizon. So kind of taking you back to the beginning, ocean effects can be really hard. And I feel like we could have continued our development and refinement process for another 6 months, a year, and still be adding interesting detail into it. Thankfully, we had deadlines that we had to stick to, so we couldn't do that. I think my wife and family would have probably disowned me if we had. But I thought I'd share the crew T-shirt with you, which kind of summarises that ongoing, always evolving process that we went through on the project. I'll now hand over to Benoit to talk about the cloud implementation.
So yeah, you might have heard about the cloud, so I hope so. I'm going to talk to you about like how we leveraged it on this project. But first, I'd like to take you back to the origin of Milk. So when we set up the studio in 2013, one of the goals was really to be able to compete against like much bigger studios. And so we identified the cloud as a technology that would allow us to reach that goal. But back in 2013, like the technology wasn't really there to like operate a full studio like entirely into the cloud. So what we did instead, we set it up with on-premises servers. But when we later opened our Milk Cardiff office, what we did is we set it up as an internal cloud, basically. So using the same technology that we would later use with external cloud providers. So by doing that, it enabled us like to be able to test all the technologies. And when we were confident that it was working, we actually started to put cloud rendering into production. So our first real project was on Poltergeist. So it was 2K renders rendered in Arnold back in 2015. On this project, we've put a couple of shots on the cloud. It was like a small scale project, like a test of the cloud, basically. So we used maybe around 1,000 cores, I think. But for us, it was more like another like test, like in this like ongoing like development around the cloud. And when that project was done, we were much more confident about what we could achieve in the cloud, and that's when we started to bid on the next like project. Which was Dinosaurs in the Wild, which is a special venue project. And that project had huge rendering requirements because each shot was 8 minutes long, 6K stereo renders, and it was all rendered in RenderMan. So for us, that really that's where we've put like the cloud at like much bigger scale. And on that project, the whole rendering was around like 6-8 weeks, and we picked at 32,000 cores. And also one thing to note is that before that we were always rendering in Arnold, and that was the first project where we diverged from that. So in terms of pipeline, we had to like develop technologies that would allow us to just be like renderer agnostic. And after that project, we went to the next stage, which was actually using the cloud, but not on like specific project, but just as needed. And a good example is when we worked on Altered Carbon. So this project was 4K renders and back to Arnold. And on that project, we didn't really think that we would be using the cloud. So we didn't do any development for that. But because there were like multiple deadlines, multiple projects delivering at the same time, we ended up doing all the 3D renders into the cloud. And after that project, we really like needed to push things even further, and that's when we started to work on Adrift. So even though it's like only 2K renders, because it was all done with Mantra, it meant like a host of new challenges ahead of us. If we're looking at our cloud setup, so we have a dedicated 10 gig line from SONET, from our on-prem data center back to the cloud. We are always using interruptible nodes, so you might have heard them mentioned in today's talks. So in the AWS world, these are called EC2 spot instances. So we do that because they are a lot more cost effective than the other types of instances. One thing that's really important, and I think that's quite different from other studios, is that the render nodes on-prem or in the cloud are actually seeing the same exact shared file system. So, and that's using a solution by Pixit Media based on GPFS. So basically, we have a Pixstore server on-prem and then multiple Pixcache servers in the cloud or in our Cardiff office. And then we use Deadline to manage the farm and all the render nodes. One thing also to note is that we recently started to use the Spot event plugin in Deadline. And what this plugin does is basically it connects directly to the AWS Spot management system, and it automatically start and stop the nodes for you. So basically, you don't even have to select like, oh, I want to start these 50 render nodes or whatever. It just does it for you based on demand and a set of predefined rules. Really, what the impact is on the pipeline when using the cloud is because we are always using interruptible nodes. It means that everything that we do on the cloud needs to be interruptible. And and it's even better if you can like use checkpoints, and so you're not actually wasting any money just on re-rendering the same frame. But it has also an impact on all our scripts. So whatever we run in the cloud means they can be interrupted. So that has a lot of implications in terms of pipeline. The second thing is the scale, which is a bit obvious, but when before it would take like years to grow your infrastructure, your render farm, like everything would grow together. But now, like just on you're starting a project, and this one has much bigger rendering requirements, and with just the click of a button, like suddenly you have like 10 times your render farm. So that has a lot of implications on your license servers, your database, everything. But basically, these 2 points we kind of like covered them in like previous projects before starting to work on Adrift. So we were kind of like we knew what to expect on this project, but what we didn't really like expected that was a lot of new like challenges were all the data transfers. So because we're using a shared file system, basically for all the scripts that run in the cloud, they see all your files, but maybe the data is not there yet. So that has an implication. So what we would see like in the studio is like, for instance, we would see idle nodes on the cloud waiting for data, which is basically like wasting money. So it's better if you can avoid that. Or we would see jobs on the render farm on-prem working on files that haven't come back yet from the cloud, which means like you can have like corrupted data or like jobs just failing. And what we would start to see is also like artists constantly asking us like, when are my files back? Because I need to review them. We need to like do a dailies. Are the files there? Is it missing maybe one frame? And they didn't have any information. So that's what in the pipeline we thought, okay, we have some issues to fix. So first we looked at where these issues were coming from. So if we're looking at the cloud rendering here, a simple diagram. So we have our on-prem servers, we have the rendering happening in the cloud, and basically these rendering processes are querying data from the file system, which means that we have to upload some assets, and then the rendering process is rendering images, which are coming back from the cloud. So that's pretty like standard. But what would happen on Adrift is, as James was showing earlier, we had these huge particle caches, like geometry caches, and that meant that, especially on like long shots, like the 3,000 frame long shots, you end up having like gigs and gigs of data to upload, and then you have a bottleneck basically. And on the other direction, because the deadline was very tight for that project, we had to pile up all the jobs, we had to scale up the cloud usage, which meant we had like thousands of frames to retrieve from the cloud, and that was another bottleneck. One thing we didn't really think at the beginning of the project as well is because we were using all these checkpoints for interruptible nodes, is especially in Mantra, the checkpoint files are quite huge, and Mantra is constantly writing into them. And with our shared file system approach, it means that these files would constantly get synced back to our on-prem server. So to alleviate all these issues, we started to work on a few solutions. And just a few words about the pipeline team. We are a team of 4 developers and supporting multiple shows at the same time, and Adrift was one of them. So we had quite limited resources to just tackle all these problems. So the first solution we developed was, so if we're looking at the Houdini scene here, so we have 2 Mantra nodes connected to our farm submitter node. What happens when the artist is actually submitting the job? So if we're just looking at one of the nodes, it gets translated into a render job on the farm. So render job is basically just a collection of frames independently being rendered, but we just represent it as one unit. So what we did is develop a custom node inside of Houdini, which we call the cloud cache, that the artist would manually create and connect to their Mantra nodes. And then the artist would, in this cloud cache node, put all the files that they needed for the render. And then when we submit the job to the farm, we transfer this list of requirements into a file that we will then use in a pre-job script in Deadline. So that's basically an extra task that gets added before the job can run. And what this pre-job script is doing is basically querying all this data. So what happens is, before, what we would see is maybe 50 render nodes starting in the cloud, and all of them waiting 20 minutes for data to arrive. So you've just wasted 1,000 minutes in cloud rendering. So with this approach, we just had one node spending 20 minutes to query all the data, and then we can start all the render. Which is basically what it says here. The second solution was to prevent the checkpoint files from being synced back. So we still really need these checkpoint files because we want to be able to resume jobs. But we thought oh, actually we need the checkpoint files, but maybe we can just store them in the cloud, but not sync them back. So to do that, we created a location in the cloud that's separate from the shared file system. And what we then did is, if we're looking at the bottom is a representation of the jobs on the farm. So we have an export job on the left and the Mantra render job on the right. So what the export job is doing is basically creating the scene description files, the IFD files, that then gets rendered in Mantra. So what we inserted is a pre-task script, which will run for every single IFD file. And what this pre-task script is doing is basically editing the scene description file. And if the job is running in the cloud, is dynamically changing the checkpoint location. So if the job is running on-prem, then we have the same behavior as before. But if it's running in the cloud, then we can redirect the checkpoint basically to be stored locally and not synced back. And the last thing we did in pipeline, so if we're looking here at on the left, we have a render job. On the right, we have a post-process job. So these two jobs would happen one after the other. And so it could be, for instance, on the left, we could have tile rendering, multiple tiles, and then on the right, a merge tile job. Or it could be maybe a render job, and then on the right, a publish job. So what we don't want to happen is the job on the right shouldn't start before all the files are actually back from the cloud. So to achieve that, we actually added, thanks to Deadline API, we added a couple of callbacks into the jobs. So the first one was adding a post-task script to the render job. And what this post-task script is doing is, for each frame, it connects to a database stored on premises, and it stores some metadata information for each frame. So for instance, we have the file path, we have the date and where it was rendered, and then what's important is we also store the file size. So then what we did is adding a script dependency to the post-process job, which is a mechanism in Deadline that allows you to control exactly when jobs are actually starting. And what Deadline will do is constantly ask, oh, can I release this job? Can I release this job? So you can actually control that. So what we did is this script dependency would actually compare the file sizes between what's stored in the database and what's stored on the on-prem file system. And until the file size is matched, it just doesn't start the job. And when the file size is finally matched, then it can actually release the job. So what this means is we know that when the post-process job runs, it has all the data it needs. And one thing we added is also a pre-job script on the post-process job, which actually does a more like in-depth check of the frames by checking their MD5 hashes, which means that finally when the post-process job runs, we know that all the files have been back and that none of them are corrupted. And also what we did is adding some artist-facing tools. So directly from the Deadline monitor, they can like actually check, they can open a GUI and the GUI will tell them whether the files are back from the cloud or if it's still missing some. If we're looking at the previous projects I mentioned before here, so we see the number of cores that we picked at, and on Adrift, so with the scale of the project and the deadline we had, we knew that we had to push things farther, and thanks to like some of the solutions that I explained before, we managed to reach an average of 80,000 cores over the whole rendering, which lasted 8 weeks. And on the last 2 weeks, we actually peaked at 132,000 cores. So, which might not be the biggest number that you'll hear today, but I think what's important is that even on like small scale productions and with like limited resources, like small teams, you can actually achieve like really like huge like renders like that. And what's next for us, basically, like when I describe the cloud cache node in Houdini, what we want to do is, instead of relying on the artist telling us what data they need, what files they need, is actually we have all the data in the scene. So just have an automatic way of like getting all that information, and also have that available if we're using Mantra, but also if we're using RenderMan or Arnold. What we're looking at next also is start to store in the cloud some long-term storage. So for instance, if we're using Maya 2018 now, we have some copies of Maya 2017 on the file system, but no one is really using them. We don't want to archive that on tape. We don't want to delete that. So why not just like storing all that into the cloud? And if it's needed, then we retrieve it back. And finally, like a lot of companies, we are looking at using the like workstations directly into the cloud. And now we are open to some questions. Yep.
With the use of the MD5 hashing, did you guys run into any collisions? No, thank you. With the use of the MD5 hashing, did you guys run into any collisions?
No. Yeah. No, we didn't see any collisions, and yeah, we used it because we had a couple of occasions where we would get corruption, but we didn't know where it was coming from. So that really helped us to actually locate. Was it like the renderer like fading in the cloud? Was it like the connection back? And that allowed us to exactly know what was happening.
And one second question is, how many of those 132,000 cores were to multi-thread the flip solvers versus user rendering?
Actually, maybe I didn't mention it, but all the FX simulation were actually done on premises. And then we did all the rendering. That's right.
Yeah, correct. Yeah.
So the 132,000 cores were only doing Mantra render jobs. So we didn't do any FX simulation directly into the cloud. Because there were like a lot more I/O involved, and we really wanted to put like all the multi-threaded like CPU, like big usage like of the rendering into the cloud.
Hey, how did you guys sort of manage costs and not letting jobs run out to, using thousands of cores for, no good reason?
So we had like daily meetings with between production, finance, and the systems team, just to like monitor like the cloud usage on a day-to-day basis, and see with production like to see what are the needs were, and what we could afford, basically based on the budget.
Not an easy part of it, for sure.
Yeah,
and I think something we're still learning about how best to do that ourselves. We feel that we had these regular meetings and just trying to communicate as much as possible there, but we felt the scope of the project changed across the project. Like I say, the non-linear side of the shot pipeline meant a lot more renderings. We had to keep our eyes on that, re-renders of stuff. Shots expanded to be even bigger than we thought they would be at the start as well. So there was a lot of factors that made it a tough project from that point of view, and it did have the potential to sort of explode. But yeah, I think communicate as much as possible in these regular meetings are the key there.
And did you render check frames to begin with, or did you render everything? Like I guess putting everything in the cloud kind of shows you the cost then, very obviously, of like bad renders and failed frames and so on. Did you just kind of blindly submit everything and hope that it would come back well?
No. With this continued development thing and developing throughout the shot process, it wasn't ideal, and it was kind of hard to predict all the time. But we still have on-prem resources, so we would be able to do our sort of render checks and get a good idea of the kind of lengths of time we're talking about. So it was a tight time scale to work with, so it wasn't always possible. It wasn't that ideal case where you know exactly how long it's going to take. So it was a best guess, but we were trying to check as much as possible locally before we just cranked up the numbers on the farm, on the cloud, sorry. Okay, thank you.
Thank you.